Welcome to the deep dive. Today, we're taking you behind the scenes of hydraulic fracturing,
Mm-hmm.
but not the part you hear about in the news.
Why?
We're getting into the nitty-gritty of the fluids
Okay.
used to crack open those shale formations.
Interesting.
You've sent us some fascinating excerpts from a textbook
Okay.
called Hydraulic Fracturing,
All right.
which give us a peek into this complex world.
It's easy to get lost in the political debates,
Yeah,
but understanding the actual engineering
right.
behind fracking can give you a whole new perspective.
For sure.
We'll break down the components of these fluids,
Okay.
how their properties are measured,
Yeah.
and why that matters
Okay.
for both effectiveness and environmental considerations.
The first thing that jumped out at me was the focus on water.
Okay.
I mean, it seems obvious that you'd need water,
Sure.
but the text emphasizes how the type and quality of water used can make or break the whole process.
The excerpts mention filtration levels,
Okay.
down to 2 microns for some applications.
What?
That's incredibly fine,
Really?
much smaller than a human hair.
I had no idea.
And the source of the water matters too. Using seawater has its own challenges,
Okay.
like the potential to fuel bacteria growth in the reservoir.
Hold on. Bacteria growth.
Yeah,
Miles underground.
right.
That's not what I pictured.
It highlights how crucial the chemistry is.
Okay.
Seawater contains sulfates,
Right.
which can react with certain minerals in the shale and create the perfect environment for bacteria to thrive.
Oh, wow.
These bacteria can produce corrosive byproducts
Oh, no.
or even clog up the well,
Wow.
hindering the entire fracking operation.
So using seawater adds a whole other layer of complexity.
Yeah,
What about using recycled water?
Sure.
I know that's becoming more common.
absolutely. Reusing flowback water makes sense from a conservation standpoint,
Right.
but it definitely adds complexity to the fluid design.
Yeah.
That water already contains various chemicals and minerals from the fracking process. So ensuring its compatibility with the new fracking fluid
Okay.
is a critical challenge.
So it's not just about pumping any water down there.
No.
It's a carefully calculated cocktail.
You got it.
The excerpts also mention clay control agents.
Yes.
What exactly is their role?
Think of shale as a dense layer of rock
Okay.
with tiny clay particles within it.
Right.
When you inject fracking fluids, you don't want the water reacting unpredictably with those clay particles.
Okay.
It could cause the well to collapse
Oh,
or make the fracking process less effective.
got it.
Clay control agents like potassium chloride or specialized organic compounds
Right.
help prevent this by stabilizing the clay
Oh.
and preventing it from swelling or migrating.
So it's about managing the interaction between the fluid and the rock itself.
Yeah.
Okay. Makes sense.
Mm.
Now, the source material dives deep into viscosity.
Right.
They make it clear that getting the viscosity right is crucial,
Yeah.
but also really tricky. Viscosity is basically the fluid's resistance to flow.
Yes.
Think about honey versus water. Honey has a much higher viscosity.
Right.
In fracking, you need a specific viscosity
Nah.
to effectively carry the proppant,
Yeah.
the sand that keeps the fractures open deep into the rock formation.
Yeah.
So if the viscosity is too low,
Yes.
the sand just sinks to the bottom
Right.
and can't prop open the fractures.
Exactly.
And if the viscosity is too high,
Yeah.
you risk creating fractures in unintended directions,
That's right.
which could lead to some serious consequences. Like what
Yes.
kind of consequences?
Well, if the fractures grow in the wrong direction, they could potentially reach groundwater aquifers
Oh, no.
or even other geological formations.
Okay.
This could contaminate the water supply
Wow.
or even trigger seismic activity.
Whoa. So it's not just about efficiency.
Right.
It's about safety, too.
For sure.
It sounds like a delicate balancing act.
It absolutely is.
And to make things even more challenging,
Yeah.
the source material highlights how difficult it is to accurately measure and predict viscosity under the extreme conditions found miles underground.
It's a big challenge.
Yeah, there was a section about measuring viscosity that went completely over my head.
Really?
All that talk about shear history simulation and the Weissenberg effect,
Okay.
it felt like a different language.
Those are some of the specialized methods scientists use
Okay.
to understand how fluids behave under stress.
Ah, interesting.
It's complex stuff.
I can imagine.
But the key takeaway is that the way you measure viscosity in a lab
Okay.
might not reflect what actually happens downhole,
Right.
where the temperatures and pressures are extreme.
Makes sense. So even getting reliable data on these fluids is a challenge in itself.
You got it.
No wonder they spend so much time on this in the textbook.
Right.
It's all about making sure the fluid behaves exactly as intended,
Yeah.
even miles underground. So we've talked about water clay control agents and viscosity.
Mm-hmm.
It's incredible how much goes into just these basic components.
It's a lot.
What about the proppant itself?
Sure.
The text mentions Stokes' law
Okay.
and how proppant actually falls through the fluid. I thought the whole point was for the fluid to carry the proppant.
That's right. The fluid is the carrier,
Okay.
but it's a constant battle against gravity.
I see.
Stokes' law basically describes how fast a particle will settle in a fluid. It all comes down to the balance between the proppant size and density,
Okay.
the fluid's viscosity, and the forces at play downhole.
I see. So even with the right viscosity, there's no guarantee the proppant will reach its destination.
Right.
It's like an obstacle course for those tiny sand particles.
Exactly. The source material even gives an example where the effective viscosity needed to transport the proppant effectively was much higher than you might initially think
Oh, wow.
because of all these factors at play.
That really highlights how much precise calculation and prediction goes into designing these fracking fluids.
Yeah.
It's not just a mix-and-go situation.
No, it's not.
We've covered water, clay control agents, viscosity, and proppant.
Right.
Are there any other key ingredients in this fracking fluid cocktail?
The source also talks about the need to control bacteria growth.
Right, because we were talking earlier about how seawater can introduce bacteria into the shale formation.
Exactly. And even with freshwater, there's always a risk of bacterial contamination.
Okay.
These microbes can create all sorts of problems downhole.
Like what?
They can produce corrosive byproducts that damage equipment,
Oh.
or even eat away at the proppant, reducing its effectiveness.
I see.
And in some cases, they can form biofilms
Okay.
that clog up the wellbore,
Wow.
essentially shutting down the operation.
So you need to add something to kill these bacteria.
That's where biocides come in.
Okay.
These are specialized chemicals
Yeah.
designed to eliminate or inhibit bacterial growth in the fracking fluid.
It's fascinating how you have to think about a whole mini ecosystem existing miles underground.
I know, it's wild.
You have to control the clay, the viscosity, the bacteria.
Right.
It's amazing how much engineering and chemistry goes into this.
Absolutely.
Speaking of controlling things,
Yeah.
the source material also mentions something called breakers.
Oh, yeah.
What are those?
Breakers play a crucial role in the later stages of fracking.
Okay.
Remember how we talked about needing that high viscosity to carry the proppant deep into the formation?
Right.
Well, once the proppant is in place and holding the fractures open, we actually want the fluid to become less viscous,
Oh.
so it can flow back up the wellbore more easily.
Oh, so it's like a time release mechanism for the viscosity.
Exactly. Breakers are chemicals designed to break down the gelling agents
Okay.
that give the fluid its high viscosity.
Interesting.
They can be activated by different triggers like time, temperature, or even changes in pH. Once the breakers are activated, the fluid thins out,
Okay.
allowing it to flow back up to the surface,
Right.
leaving the proppant behind to keep the fractures open.
So it's like a carefully choreographed dance of
It
chemistry.
really is.
High viscosity to get the proppant in place. Then a quick change to low viscosity to get the fluid out.
Exactly.
This source also mentions something about friction reducers.
Yes.
I'm guessing those are important for getting the fluid down the well in the first place.
You got to think about pumping a thick fluid thousands of feet down a narrow wellbore.
Yeah.
There's going to be a lot of friction.
Right.
Friction reducers are chemicals designed to reduce that friction,
Okay.
making it easier to pump the fluid and requiring less energy.
Makes sense.
This not only saves money,
Right.
but also helps minimize the risk of unintended fractures.
That makes sense. So less friction means less pressure is needed to get the fluid down, which reduces the chance of creating fractures in the wrong places. It seems like every component of these fluids has a very specific purpose and plays a crucial role in the overall success and safety
Absolutely.
of the fracking process.
You're absolutely right. And what's fascinating is that the science behind these fluids is constantly evolving.
Oh, wow.
There's ongoing research into developing even more sophisticated additives,
Okay.
like those designed to prevent scale buildup.
Scale buildup. What is that?
Think about what happens inside your kettle if you boil hard water.
Okay.
You get that white, crusty buildup of minerals.
Right.
A similar thing can happen in fracking wells. Certain minerals in the water can precipitate out and form scale deposits on the equipment.
I see.
and inside the fractures, hindering the flow of fluids.
So you need to add something to the fracking fluid to prevent this scale from forming.
Exactly. Scale inhibitors are chemicals designed to prevent these mineral deposits from forming,
Okay.
keeping the wellbore and fractures clear for optimal fluid flow. And as for enhancing proppant flowback,
Yeah.
researchers are developing new types of proppant coatings that allow the proppant to flow back more easily with the fluid
Okay.
once the fractures are established.
So instead of getting stuck downhole, the proppant comes back up with the fluid,
Yeah,
potentially reducing the amount of proppant needed
right.
and minimizing the impact on the formation.
Precisely. It's all about optimizing the process
Mm-hmm.
and reducing its environmental footprint.
Okay.
And that leads us to another exciting area of research:
What's that?
biodegradable fracking fluids.
Oh, yeah, I remember reading about that.
Mhm.
So instead of leaving potentially harmful chemicals underground,
Yeah,
they would simply break down naturally over time.
that's the idea. Traditional fracking fluids contain a mix of chemicals,
Okay.
some of which can persist in the environment for a long time.
Right.
Biodegradable fluids are designed to break down into harmless byproducts through natural processes like microbial activity or exposure to sunlight.
That sounds like a win-win.
It could be.
Less environmental impact and a more sustainable approach.
Right.
But I imagine developing these new fluids is a huge challenge.
It definitely is. Balancing biodegradability with performance. And cost is a delicate act.
Yeah.
These fluids still need to effectively carry proppant control clay and withstand extreme conditions downhole,
Right.
all while being environmentally friendly.
I can see how that would be a tough nut to crack.
It is.
But it's exciting to think about the future of fracking
Mm-hmm.
and how these advancements in fluid technology could lead to more sustainable practices.
Absolutely. It's a field that's ripe for innovation.
Okay.
And it's crucial that we continue to explore these possibilities.
It's mind-blowing to think about all the science and engineering
Oh, right.
that goes into something most people never even consider.
Right.
The fluids used in fracking, it's a hidden world of complexity.
It really is. And we've only just scratched the surface. There's so much more to explore in terms of the chemistry, the environmental considerations, the economic implications.
Sure.
It's a fascinating field that's constantly evolving.
Yeah, this has been an incredible deep dive. We started with what seemed like a simple topic,
Right.
water,
Yeah.
and ended up delving into a whole universe of specialized
I
chemicals.
know, it's wild.
Complex calculations and cutting-edge research.
It really is. And all of that is happening miles underground,
Yeah.
under extreme pressure and temperature.
Right.
It's a testament to human ingenuity and our ability to solve complex challenges.
For sure. So for our listener,
Yeah.
someone who's interested in fracking, but maybe hasn't considered the fluid side of things, what's the key takeaway from all this?
I think the biggest takeaway is that understanding the technical aspects of fracking
Okay.
can empower you to have more informed conversations about the process.
Right.
Whether you're talking about the environmental impacts or the economic benefits, understanding the science behind the fluids is crucial.
It allows you to see past the headlines and the political rhetoric and form your own educated opinions based on facts.
Exactly. And it can also help you appreciate the incredible engineering feats that make fracking possible.
For sure.
It's not just about digging a hole and pumping stuff down there.
Right.
It's a highly sophisticated process that requires a deep understanding of chemistry, physics, and geology.
It's a reminder that even seemingly mundane things can be incredibly complex and fascinating when you take a closer look.
Absolutely.
And that's what the deep dive is all about,
Right.
uncovering those hidden layers of complexity and making them accessible to everyone.
We've talked a lot about the composition of these fracking fluids,
Yeah.
but it makes you wonder,
What's that?
how do they actually monitor what's happening miles underground?
Oh, that's a good question.
How do they know the fluids are behaving as intended? And what kind of data do they collect during and after the fracking process? That's something to ponder.
That's a great question to leave our listener with. Until next time, keep those curious minds engaged.